This is the second part of Experiment 16 from Make Electronics, second edition by Charles Platt. We'll be looking at the bistable mode of the 555 timer in just a few minutes, but first let's go back and look at the monostable multi-vibrator. For our convenience, I have soldered this circuit up so I can go around and probe it. You can do the same thing by attaching your voltmeter probes to some small wire leads and inserting them in different parts of the breadboard. And I'm just going around and checking the power, making sure that I have 9 volts. Now what I'm going to do now is go and sit on pin 2, which as you recall is the input or trigger, and notice it reads 9.4 volts. Until I press the trigger button, it goes down to 2.9. Alright, so it's pressing the A button. I get a number which is just below 1/3 of the control voltage of about 9 volts. Let's grab a small screwdriver and adjust that threshold pot just a little bit. I'm going to say move it clockwise a little bit. I always leave the common probe in the negative rail. Then I check my power and then move my probe to where I want to measure, in this case pin 2. Now right when I touch it, I might accidentally discharge the timer, so I wait for that to end, and then I'll press it again. And remember, I moved the pot a little bit, and it's now 3.68. Notice the timer is not triggering at 3.68. And that's because 3.68 volts is greater than the battery voltage, currently about 9.3 or 9.4, divided by 3. Let me adjust that pot just a tiny bit closer to the triggering area. It'll get a little bit of a transient right when I touch it. Ignore that. 9.36 down to 3.24. Boy, that's just not quite enough to trigger. I have to actually adjust the potentiometer so that I meet the trigger condition. Here we go. Not quite. Yes, 2.8. So just less than 1/3 of VCC. We'll just test a little bit more. Twist it farther counterclockwise, going to lower and lower voltages. Now it should really have no time triggering once I press the button. Here we go. 0 volts absolutely triggers it, much less than 1/3 VCC. And I'll leave it at some little intermediate region. Right there should do it. Should give you a nice hefty trigger pulse. 0.45 volts, again, definitely less than 9.3 divided by 3. Now I'm going to take a moment and investigate the reset pin. So again, I've got my common voltmeter probe on negative, and I'll go over to pin 4, which is the reset. Now remember that I'm pressing with my other hand here the reset button, which is push button B. So normally it's held high by a voltage which comes to it via the 10 kilo ohm resistor until I push the button which connects that pin directly to ground. Doesn't short the circuit because of the 10 kilo ohm resistor, which we call a pull-up resistor. That is, it keeps that pin high until I want to reset the circuit by pushing B. Okay, finally let's go and explore the upper potentiometer going into pin 7, the threshold. Now notice that after I press the pulsing button, the trigger button, the voltage changes. It raises up from 0 until it gets to 6 volts, which is about 2/3 of the supply voltage. There it goes off right when it hits 6. Again, this is the design of the 555 timer, regardless of the time constant. When it hits 6 volts, the timer goes off. I change that time constant by changing the effective resistance in that upper pot. So it always goes off at the same voltage. It's just a matter of how fast it gets there. That case was very short, went out quickly, but still reaching almost 6 volts. There just flashed for a moment, faster actually than the voltmeter could even respond. Now I'm going to do a little experiment where I hold the A push button, the trigger push button in for a while. Past the 6 volt, it keeps charging, the light stays on. And if I wait, it should go all the way up to VCC, or almost get there, and when I release it, it'll turn off. You can see that what the A button does is it starts the capacitor charging, and the timer interprets the 2/3 value of VCC as being the level at which it should stop the output. Let's take a look while I have soldered this board together. Again, it's something you don't need to do for the class. I'm going to show off a socket for an integrated circuit, an IC socket, which allows me to slip in and out the most precious thing on the board and the most easy to damage, which of course is the 555 timer itself, just as if it was going into a breadboard. So I get the pins nicely, neatly lined up. I push it right in. The advantage of a socket is that I can solder to the socket, not worrying about heat damaging or solder damaging the precious integrated circuit. Of course, the 555 timer itself isn't particularly expensive, but the more electronics you do, the more expensive ICs you often end up using. So that's a way to preserve them. Okay, let's go on and look at the bistable mode of the 555 timer. I've built the circuit shown here. The idea of a bistable mode is to use only the flip-flop portion of the 555 integrated circuit. I've just been discussing how the discriminators work. The trigger discriminator goes high when the input is less than 1/3 of VCC, and the threshold discriminator goes high when it gets a value that's greater than 2/3 VCC. Now the discriminator output goes to this flip-flop element, which we've isolated in the circuit, and the flip-flop determines the output of the whole circuit. Now in this flip-flop only mode, what happens is that we ground the threshold such that it never reaches 2/3 VCC, and therefore the pulse lasts forever. So we've made a timer circuit with no timing, and as you can see, we're just waiting for it to turn off. The only way to turn off the LED is actually to press the second pin. So we turn it on, we wait as long as we want. It holds this fact that we pressed the first switch in memory until we clear it with the second. Now we can click the second button all we want. It's not going to change state until we hit the first again. We can keep hitting the first, and it keeps that binary 1, that on signal, in its memory until we actually reset it. So what is this circuit good for? Well, it does represent a single bit of memory, and it's the way that the 555 timer keeps the information around about what has happened in the past. In other words, which thresholds have been exceeded. Was the trigger most recently exceeded, or was the threshold most recently exceeded? And by keeping that information in memory, it's able to say in the monostable mode, keep a pulse on for a certain amount of time. In the bistable mode, keep it forever. And as we'll see in the final portion on the 555 timer in experiment 16, we'll actually keep it on for a brief amount of time, and then off for a brief amount of time, and then go back to the beginning, creating an oscillator. What I'd like you to do now is to, I think you're adequately prepared to watch a full-length video on how the 555 timer IC works. It was prepared by the website Intro to Mechanitronics. Please watch this video. It goes in some great detail about the inner workings of the 555 based on what we've learned so far. With that done, you're ready for the 16B assignment. The first is to, after building this simple circuit, explain why it is the flip-flop is sometimes called a latch. Some hints about this in the textbook. And this should explain how it can be used to store digital information. In the second part, I'd like you to actually go online and do a little bit of research. and show how the knowledge that you've gained in this course can be used to understand more things in the world around you. That's the goal. And in particular, let's look at SRAM, or static random access memory, versus DRAM, or dynamic random access memory, which are two different types of memory which you would be very concerned about if you were specifying a particular computer to buy. I will give you the simple hint that SRAM is made of flip-flops, whereas dynamic RAM typically uses simply transistors and capacitors instead. Do some research on SRAM versus DRAM, where they're used, and try to write up a layman's explanation, or how you would explain the different components and what they mean for the performance of this memory if you were buying a computer. So